is actually looking further into rectilinear motion. So yesterday, I talked to you about the difference between displacement and distance. All right? Now, can you tell me which one actually has a direction attached to it? I was talking about distance and displacement. Displacement, thank you. So, you should recall that with displacement, it could be a positive direction and negative direction. Correct? Yeah? And also, when we are talking about rectilinear motion, it's a 1D motion. Alright, so therefore you can go forward and come backwards. Yeah? Go forward and backwards, and it can change in direction. It could even change, for example, if you're walking, positive, change to negative, and then change back to positive again, and then change back to negative, and just sort of going up and down. Now, the displacement is changed, but there will be a total distance. Correct?
Yes.
Yes. Yeah?
Yes.
And velocity is a vector quantity.
Yes.
Speed is not.
Yes.
So you've got to remember that one has direction, one does not. Now, what we're going to do today is I'm going to start you off with second derivatives. Then I'm going to link second derivative to the acceleration, and then finally interpret graphical significance. So second derivatives linking to acceleration, it's going towards year 12. So I will, like I say, I will show you what a second derivative is, and I will show you how to use second derivative. But I do expect you all to do the sign test in the exam. Alright? Now that you don't have any more assessment, no more tests, I do expect you to do the sign test, alright? But you will learn what second derivative is. So then you need to know that acceleration is actually the second derivative of a displacement function with respect to time, which is the first derivative of a velocity function with respect to time. Then you need to link the knowledge of calculus to displacement time graph and identify the gradient function of position time graph as velocity, and finally examine velocity time graphs and their relation to displacement acceleration. Alright, now what is second derivative? So you know that for the function function y equals fx, you can write the first derivative as dy dx, which is f dash x, correct? Yeah? So the next thing you need to know is we can, from the gradient function, and derive another gradient function, the gradient of the gradient function, the gradient function of the gradient function, which is a second derivative. So the second derivative is the derivative of the first derivative, which can be denoted as d2y and dx squared. Alright? This is basically just, if you write it out, it's just d dx dy dx. Alright? And then is f double dash x. Alright, so second derivative. So once you've derived your dy dx, and then you use the same idea and derive your d2y dx. All right. Now, I'm going to go into this one, which you will learn next year, but I'm going to go through it very briefly. You can use a second derivative to determine the local extrema of a functions under certain conditions only. All right, only under certain condition. If dy dx equals to 0, you know that it's either local maximum or local minimum, correct? All right, or a horizontal point of inflection. If it is greater than 0, d2y dx squared, if it is greater than 0, when dy dx equals to 0, then the function has a local minimum there. Whereas if dy dx equals to 0 and d2y dx squared is negative, then fx has a minimum, maximum there. You can use this to check if you don't use your sign test. But in the exam, I do expect all of you to do sign test, and I can guarantee you we do assign marks for sign test. Alright, please make sure that you do that. And then you need to know that these are the conditions you can be used. If not, the second derivative test cannot be used for the following condition. dy dx equals to 0 and d2y dx squared equals to 0. dy dx equals to 0 and d2y dx does not exist, or dy dx equals to 0 or does not exist at all. Alright, so you've got to be very careful. Only certain conditions you can use that. Year 12. Don't do it now. I'm just showing it to you, that's all. Now, can you therefore now derive the second derivative of the following functions, please? So you can start off with dy dx and then do your d2y dx squared. Here, I would expect you to expand, all right? Which means that will be equals to and I'm going to stop here. Do it first, then I'll show you my answer. Alright, so you do use your power rule to go from your function dy, from y to dy dx, and then from dy dx to d2y dx square. Alright? So you know that this will be a cubic function. From a cubic function, the gradient function is a parabola, which is a quadratic, and if a quadratic function is there, the gradient function of a quadratic function would be a linear. Right. Yeah? So, if you think about that, if you expand it, you should get d2y dx squared of 54x minus 72 from a cubic. Taking the first derivative will be a quadratic. The derivative of quadratic will be a linear. Alright? Now, the second one, what you need to do is be able to split it into three fractions, and then from the three fractions, you need to write everything in terms of t to the power of certain index. Alright? So therefore, you can see that that will become t, 3 over 2 minus 1 is half, plus 2 plus 5t to the power of minus 1. I'm skipping step already. Alright? I did not write down everything, but I'm just starting to skip step. Can you do your second derivative then, please? Now write everything in terms of a index. Makes life a little bit easier. Alright, let me review my answer. So I've written everything in positive index, plus also change it to radical.
Oh yes, sir.
Yep.
In the test, do we have to make it a radical or not?
Not necessarily.
I
No.
said I did the thing and then I wrote 4 and then also the radical.
In this case, don't worry about it. I think unless you are asked to say to write a radical, if not, that's fine. I don't mind if it is. If you stop at here, that's fine. That's fine with me. All right, unless you're specifically asked to do radical. All right, now that you know a second derivative, I'm going to bring in the idea of acceleration. All right, the acceleration is a change in the velocity over a change in time. That is, acceleration AT is the rate of change of velocity with respect to time, which is the first derivative of velocity. Or you can say that acceleration is the second derivative of displacement with respect to time. So now let's think about what the statement here means. So when I'm talking about displacement, you know that I can go forward and backwards. Correct? Yeah? Forward and backwards. And that's direction. With that, the time taken to travel, you've got to think about whether I'm doing it at a constant velocity or my velocity is changing. Alright? If I'm doing it at a constant velocity, which means that, what is the acceleration? Zero. Alright? When you are walking at a constant velocity or traveling at a constant velocity, the acceleration is zero because there's no change in your velocity. Correct? But if I walk and then I suddenly run, there is a change in velocity. So I'm accelerating. I'm moving. Alright? Then I could be running and then slowing down, which means there is a negative acceleration, which means I am slowing down. Alright? Now, what you need to think about is you could have a positive velocity but negative acceleration, which means you're slowing down. Right? You could have a positive velocity because you are walking and then or running and then you're slowing down, you're decelerating. So it's negative acceleration. Right? So you're slowing down. Think about that. You will learn a lot more of this in year 12. There will be a whole big topic. So now what I want you to take back is the rate of change of velocity with respect to time is acceleration. Which means this is actually the second derivative of displacement. Alright, now what I want to do is let's do a few let's go through an example. So a particle has displacement modeled by the following function. So keeping in mind that velocity is the first derivative of displacement, acceleration is the second derivative of displacement. Once we are given a displacement function, we can actually derive the acceleration. So you can actually determine the expression of acceleration of the particle over time. Alright, here you were not given any units. You can see that in this case, for part A, let's do the first derivative of the displacement. St will therefore equals 12t squared minus 18t plus 3. Right? And then S double dash t, which is the second derivative, is therefore equals to 24t minus 18. Alright? So that is the expression for the acceleration of the particle over time.
Yes.
Now, part B. How do you know if the acceleration of the particle is constant? Is it constant? Is it not? Why?
It is constant.
Why is it constant? Why do you say that it is constant? So that is the acceleration. Why do you say that this is constant?
Linear graph.
Sorry?
It's constant, it's a straight line, but then it's separating. If it's constant, then it must be a constant.
It keeps on going up.
So like it's not
Does it keep on going up?
Yeah. As time changes.
No, the acceleration will go.
Okay, what if when time is 1? Is it going up, down?
Yeah.
It's going up. So, but the thing is, you cannot, looking at this function, you know that the acceleration of the particle is not constant because time is involved. Time is involved. So with the change of time, there's a change in acceleration. So when time is 1 second, it will be 24 minus 8, which is it's 6. So it will be 6 meters per second squared, and so on and so forth. So you know that time is involved, therefore the acceleration of the particle is not constant. So the way you answer it is, let me get my wording out properly. So x is a the acceleration is variable. It's not a constant.
Do you think I use calculator? That's my set. No. I said BD what is that? I said acceleration is not constant.
Alright, you have got time t's in the equation, therefore it's not constant, it's variable. Unless your second derivative is 24t, unless it's just minus 18, which means the constant is minus 18. But it's not. So now can you determine the instantaneous of particle when t equals to 3? Of course. So t equals to 24 times 3 minus 8.
72 minus 18.
18, sorry. Which is?
54.
Yep. Alright, you don't have a unit, so just leave it as 54. Now, let's have a look at example 3. An object is moving with a constant acceleration of 3.2 meters per second squared. This time you got a constant. The object has an initial velocity, v0, of 8 meters per second, and after 1 second of motion, the displacement, let's call ST, S1, is 12.6 meters. Alright? You need to determine an expression for the displacement of the object with respect to time. Now, look at what you've given. You are given that the acceleration is constant at 3.2 meters per second squared. So you know that Vt is 3.2, right? This is the first derivative of V. So therefore, integrate that. Is actually 3.2t plus c. Correct? Do you agree with me? So since we know that when V0 equals to 8, therefore C equals to 8. So therefore Vt is 3.2t plus 8. Now we can find the expression of the displacement. St equals to integrate Vt with respect to t. Therefore it's 3.2t squared over 2 plus 8t plus c, which is 1.6t squared plus 8t plus c. Correct? So now we know that S1 equals to 12.6. So therefore 12.6 equals to 1.6 plus 8 plus c. And c is therefore equals to 3. So therefore St equals to 1.6t squared plus 8t plus c. Alright? This is plus 3, not c. Thank you. Now, therefore, you can find the velocity at part B. So V2 is actually 3.2 times 2 plus 8, which is 14.4 meters per second, and displacement at 2 seconds is 1.6 times 2 squared plus 8 times 2 plus 3, which is 25.4 meters. Alright? Now, everyone, focus please. Close the laptop. You don't, yep. Hang on.
For the unit?
Sorry?
For the unit, do I have to put like...
This one you got to give unit because you've got the
Like, some extras like meter per second square over second.
meter per second over second. So some of the units, it would be your acceleration. Unit for acceleration is meter per second square, or it could be meter per second per second.
Yes,
All right.
Writing velocity, do I have to put meter per second square over
No,
second?
velocity is always meters per second. It's the distance per.
But like some factor is like meter per second square over second. When you cancel out the second,
It,
do I have to put that?
no. Velocity is just meters per second. Meter per second. Alright. It depends on context. I have to look at the context of the question. Alright. Now, let's do a quick summary. Let's do a quick summary. What do we do? What's the relationship in rectilinear motion? How do you go from xt to vt? Alright? So from here to there is differentiate. So xt is the displacement and vt is velocity, and that's acceleration. And then from xt to vt is from there to there, differentiate xt. That will be that. Differentiate, that will be the acceleration. Going back, you integrate. Alright? Or anti-differentiate. So you go back, and then you go back again. Alright? This is how you work on going from your displacement to your acceleration. Second derivative. Coming back, one integral, and then second integral. Alright. Next thing is we are going to look at the displacement time graph. Please focus. Now, what is this telling me? What is this graph telling me? You can see that for this graph, at 0, right? What happened is it's going south 2 meters and then it's going backwards, right?
Yes.
And then going forward again, and then keep going backwards. So something like this, if I'm standing at the 2 meter mark, I go backwards to 1 meters, and then I go above something like 2.5 meters, then I walk all the way until I go out of the room. Right? So this is what you can interpret the graph. You are going backwards, going forward, and going backwards. Now, let's see what we can do with the graph. Alright, can you then draw the function of Vt and At on the same graph? How do I do that? Alright, let's first have a look at these 2 points. What do they represent? What do they represent? Zero gradient. So if I want to plot Vt on the same graph, what do I do? So here I'm going to use different color. That is xt. Alright? Which is the displacement. Now, what is velocity? Velocity is the gradient function of displacement.
Yeah.
Correct? So you are looking at the gradient. So is this gradient positive or negative?
Negative.
Is this gradient positive or negative? And then is this gradient positive or negative? Negative. These two will be your stationary point. Correct? Which means if I'm plotting VT on the same graph, alright? So you know that this is the velocity. These 2 points here, the velocity will be 0. Correct?
Correct.
Yeah? And you know that somewhere between here, there will be a point of inflection. You don't know where it is. There's a point of inflection. Because you've got to go from negative, positive, and then you go back down to negative. That's the point of inflection. And there will be the point of inflection is the turning point of the gradient function. So somewhere here, I'm going to estimate it at this point. Let's say that point. All right? So I estimate it as a right center. So I know that the gradient is negative. And then turning point, and then coming down. All right? So it's sort of like it's a parabola now. Right? So this is how you draw the gradient function. Now, what about your acceleration? I'm going to plot AT here, which is acceleration. All right? How do you do that? What do you think the, hey. Now, we are looking at the gradient, right? We are looking at the gradient of this now, correct? The gradient of this here is positive or negative? Positive, and that will be negative. And that will be 0 because that is the turning point. So it should look something like this. Again, estimating, it will be, therefore, this point here will be 0, and it could look something like this. So this is AT, the acceleration, and this is velocity, and then the blue is the displacement. Alright? So I am only estimating the graph of AT, that's all. I don't know the exact, but I can tell you where the zeros are. Alright? Yeah? All happy with that?
Yes.
Now, let's look at the velocity time graph. Velocity time graph. Shh. Hey, the last one. Let's think about the velocity time graph. What does the gradient represent? Acceleration, thank you. So, when is acceleration 0? 2 to 4, because it's a flat line. The velocity is constant, there's no acceleration. Then what happened here? This is negative acceleration, which is deceleration. Alright? So you've got the particle is accelerating from 0 to 2, and then constant at 2, and then going all the way down to -6. Alright? This is how you explain the graph. Now, let's have a look. You need to be able to draw AT on the same graph. Alright? I am going to use orange for AT. So look at this. What is the gradient of this? You know this 2, this 0, and this is 2. What would the gradient of this be? Hey? 1. So the gradient of this is 1. So therefore at 1, we can draw that straight to here, 1. Right? Now, the next one. What is the velocity, what is the acceleration? when velocity is constant? 0. So the acceleration will be here, correct? And then what about the next one? What is the acceleration or deceleration of that? -4. So therefore it goes all the way down to -4. And you can only go up to here because you can't extend it any further. This is the point that it stops 6 seconds. Alright? So this is how you actually draw the acceleration on the same graph. Now, next one. Well, actually what I need to do is show you how to work out the acceleration, AT. So between 0 and 2, acceleration is 2 over 2, which is 1. And between 2 and 4, acceleration equals to 0. Between 4 and 6, acceleration equals to, let's use 2 point here, 2 minus, hang on, if I use this point and this point, it's minus 2, minus 2, minus 2, minus 2, divided by 1, which is minus 4. Alright, so you could actually work out what the acceleration is. Now, how do you find the distance? Area under the graph, very good. How do you find out the area under the graph? Hey? Maths, I know maths, but you've got triangle, one triangle here. Alright? And then you know there is a rectangle here. Correct? And then you do know that the other bit is here. And here. Alright? That is area under the graph. Alright? So you can find the area under the graph. And in fact, this is just this triangle here. Right? You can see that that is actually this triangle. These two would add up to be this. Alright? Yeah? So you can work out the area. So the area is total area under the graph. So therefore the total, you can in fact, instead of looking at triangles, rectangle and triangles, the whole thing is just a, no. How do you find the area of this?
Half base
Half of base plus the two base, half of the two bases add together and then times the height. So the area under the graph, total distance, equals to that plus this triangle, right? So therefore this is half, that is 2 plus 4.5 times the height, which is 2, plus half, which is 1.5 times 6. So therefore the total area is the total distance is 11 meters. Now, can you work out what is the displacement? Can you work out what's the displacement? What's the displacement? So here, the displacement would be this distance, take away that distance. That will be the displacement. Yeah? Yeah? So the displacement will then be, if one of the area is, this area is 6.5. This area is 4.5. So displacement will then be 6.5 minus 4.5, which is 2 meters. Alright? So I'm going to actually stop here now, and that's the end of the lesson. So hopefully what I've done is to show you what the second derivative is, and you should know second derivative, acceleration is second derivative of a displacement function. Alright? So this is actually the end of the course for 11 methods.